Okay, it makes me so sad that we're not in a class to do this, because for this lecture, I usually really enjoy having student volunteers um, acting in the front of the classroom. Like, even if we can go back next month, it's not going to be the same because we won't be able to interact physically, and this is a lot funner when I have student volunteers. Um, Today, I'll actually be using Legos to represent atoms instead of using humans to represent atoms. And number 35 is one of the more tricky things in our course, and so I'm going to spend a lot of time baby stepping this one, and you're going to need a lot of notes. I'm warning you up front. We're going to make ozone in the stratosphere, and then we're going to break it up. And before we do that, we have to agree on a few basics. Okay, they're on the screen now. First, the outer atmosphere is pretty simple. Especially before there were humans, there was almost nothing in the outer atmosphere. You should remember from the beginning of this unit that 99% of the atmosphere is really low, and we're talking above that. In that outer atmosphere, at the top edge of the stratosphere, we're talking up here, at the top edge of the stratosphere, there's almost nothing. It's a bunch of empty space. The two most common gases, nitrogen and oxygen, you should know that they're the most common, right? And, there's all types of electromagnetic radiation, including UVC, microwaves, gamma rays. There's all sorts of really strong radiation up there, but the UVC is important. The other thing you should know is something that kids usually learn early in chemistry, but this will be your chemistry band-aid. You need to know this, and you probably want to write it down. Hofbrinkel. Hofbrinkel, it's on the screen. These are the diatomic elements. They cannot be alone. The way that we usually talk about this to help students understand is they're like clingy, they're desperate, they need to be in a buddy system like kindergartners on a field trip. Clingy, desperate, buddy system. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are the Hofbrinkel elements. And it sucks, but usually if you just say Hofbrinkel a long time, you'll eventually remember it. So keep saying Hofbrinkel. Hofbrinkel, 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 Hofbrinkel. These are always found in pairs, like that. Two of them, Hofbrinkel. H2, O2, F2, Br2. Anyway, that's why we always write them in twos. Whenever we talk about oxygen, it's always O2. Whenever we talked about nitrogen in this class, it's been N2. These are diatomic. They don't like to be alone. If they were alone, they would bond with anything else. Even if it's an awkward, uncomfortable bond, they just can't be alone. If these get freed up, we label them with an asterisk. If there's a single, we put a little symbol next to that to say, whoa, look out, that's weird. Like, look over here on my screen, please. See that little asterisk? Or right there, that L shouldn't be capitalized, sorry. That asterisk and that asterisk, those indicate this is unstable. That single is gonna get stuck to something right away. You might have heard of free radicals. That is gonna bond with something else. And there's all sorts of stuff about bonding strength and electron geometry. Like, in real chemistry, you've got real explanations for this. But for apes and passing the AP test, this would be enough. You just need to understand in your head that Hofbrinkels can't be alone. If you ever see a single one, it's getting ready to make a bond. It's going to jump onto something and grab on. This behavior of clinginess is really important for making and breaking ozone. It helps a lot. So let's go make ozone. Remember, we're in the outer atmosphere. There's lots of nitrogen, there's lots of oxygen, and there's lots of radiation. Okay? Now, oxygens can be separated from each other by ultraviolet C. Remember that ultraviolet C breaks all bonds. So here's oxygen, O2. See how they're together? And those two oxygens have a perfectly good, stable bond. That's a really strong bond. But ultraviolet C can split them. And most of the time, when ultraviolet C strikes oxygen in the atmosphere, they just get back together. They can't afford to be alone. They're desperate. They go, oh my God, I got to find somebody. And they go, oh, little buddy, thank God you're there for me. And there they go. Now, usually what happens when you split up oxygen gas is you go back to oxygen gas. But remember that we're in a part of the atmosphere where there's lots and lots and lots of oxygen around. See, look at all these oxygens. So if these guys break up and these are closer, you get an awkward threesome called ozone. Now, threesomes, I don't know. This is not as strong as this one, okay? In this case, each one of these can give all their attention to the other. So there's real chemistry here about bond strength and preferential bonding and the geometry of where the electrons go. You should know that oxygen 2 is more stable than oxygen 3. And since we don't have the time to explain the real chemistry of that, you can just imagine that, you know, threesomes are a lot of work. These guys are all going to be distracted. They're always trying to divide their attention between two others. And this guy can just focus on the other guy, and they're a much stronger bond. Now, in our atmosphere, whenever oxygen is split and you get a solo, that solo is going to make a bond. So there's another ozone. And if this one is split, the closest guy happens to be another oxygen single, they're going to go back to being oxygen gas. But if these are split and the closest thing happens to be O2, you get O3. This is how ozone is made. Watch. Oxygen gas is divided into two singles, and because there's a lot of gas around, those singles will either find another single or jump onto oxygen gas to make ozone. Oxygen is always being broken up into ozone. Ozone is self-healing because sunlight. So in the outer atmosphere, ozone is always being made. Ozone depletion, the idea that there's a hole in the ozone layer, heals on its own. You don't have to do anything. You just wait for ultraviolet to hit more oxygen gas, make more free radicals that find oxygen gas, and make more ozone. And the ozone hole closes itself up. Remember also that there is real chemistry. We just use all this innuendo as a way to keep your attention and make this behavior easy to visualize. If that's not necessary, look, there you go. High energy ultraviolet splits oxygen gas. You get two free atoms, which is pretty rare. They're not going to be free for long. They're desperate. So they collide with other oxygen around and they make ozone. If you want, there's like your pattern of electrons. And if you want, here's another way to write the reaction. Now, we need to break ozone next, but I want to take a break in this lecture so that in your head you can separate making ozone and breaking ozone. Close your eyes, look at your notes, stretch your legs, come back and watch breaking ozone separately. It'll be the same old me and it'll be the same Legos, but